Hello, everyone. My name is Atalay Kutlay. I'm a senior software engineer at Akamai's network optimization team, where I focus on increasing Akamai's global fleet efficiency. So you may know Akamai as a CDN company, but we're also a cloud provider now. We're in more than 40 data centers along the world, where customers can create virtual machines, block storage, object storage, along with other products. And as a cloud provider, it's our responsibility and our SRE team's job to keep our global fleet healthy and up to date. So this requires being on top of never-ending kernel, OS, and firmware updates, as well as doing some preventative hardware maintenance before issues happen. And in most of these cases, the host needs to be rebooted, and that can only happen once all the VMs are off of the host. In a typical maintenance, you have an old version host and you have some spare capacity that's already upgraded to the newest version. The first step of the maintenance is to notify the customer and wait for the agreed notification time. And then the migration start. And once the host is empty, now we can update the old host with the new software. And if everything goes well and the software update is successful, then the old host now becomes a spare capacity so that we can do it one more. And now another host can migrate to this new spare capacity host, and we can keep doing this forever. And this process continues until all hosts in the data center are updated. So for one host, this sounds pretty simple, but the actual challenge of the hypervisor maintenance at scale starts when you need to do a large number of these updates at the same time. Imagine yourself as the SRE team that owns this fleet. Now on Monday morning, your boss comes and tells you that there's a new kernel version that has an important fix, and we need to roll that out to 10,000 hosts. There is no light patch, so the host needs to be rebooted and the VMs need to be migrated. Because of the migration, customers need to be modified through APIs and metadata, and we have only 90 days to do this. So this sounds complicated, but we take it one step at a time. So 10,000 hosts in 90 days, that means roughly 100 hosts a day need to be updated every day for the next 3 months. So when you try to come up with that 100 hosts, you run into 3 major issues. The first is capacity. We're running VMs around, so we need to find enough capacity and specifically updated capacity for those VMs to go to. At the same time, the data center cannot run out of capacity because that would mean preventing new customers from creating VMs, and that means revenue loss. So the maintenance can only use the capacity that we budgeted for maintenance and not the public capacity. The second problem is conflict. Customers expect some tolerate some disruption in a cloud environment, but during a planned maintenance, any extreme disruption is not acceptable. Because we're trying to evacuate a lot of hosts at the same time, there is a risk of impacting some customers unfairly or asymmetrically. This is challenging for us because each host may have hundreds of customers, and the same host being evacuated can cause different levels of disruption to different customers. A large customer that has thousands of VMs in the data center may not care too much about a couple of VMs going down. However, there could be a customer on the host that has only a couple VMs, and that could be their whole infrastructure. So if the host selection is not done cleverly, you can end up in a situation like this where you take down someone's VB replicas all at the same time. The third problem is concurrency. Migrations are resource-intensive processes. They basically copy large amounts of data over the network from host to another. It uses CPU, disk I/O, and network bandwidth on the host, as well as the bandwidth of the top-of-rack router. So if too many migrations happen at the same time, you can cause network bottlenecks, performance issues, or you could even cause the migrations themselves to fail. So the host selection must also account for the physical limits of the data center. So with these 3 problems, maintenance becomes a complex task. How can we solve it? One option is to put a bunch of data on a spreadsheet and try to find a set of hosts until you find a list that satisfies your criteria. I'm not saying you can't do this, but this takes a lot of work. And because maintenance is continuous work that never ends, this would mean that you're going to do this for the rest of your career. So obviously we don't want that. We want some automation. So why don't we write an algorithm that finds a set of hosts, checks all these constraints that I talked about. This is easy to say, but hard to get it right. And it's for two reasons. The first is when you write an algorithm, you don't know how good your algorithm is. If your algorithm tells you that you can update a data center in 100 days, you don't know if you could do it in less time, unless you come up with a better algorithm. And the second problem is it's hard to write such algorithm to be flexible enough for changing constraints that may come up with a new product launch or changing business constraints, maybe due to a new customer arrival. So what is the solution? The solution comes from operations research. OR is a field that's been providing ways to model and solve complex problems to improve decision-making processes. And mathematical optimization is a fundamental tool in OR. So what is mathematical optimization? Well, to explain it in 2 minutes, I'm going to use a metaphor. Think of a genie. A genie is capable of giving you anything you want as long as you can imagine it and articulate it. So if a kid finds a genie, he asks for ice cream. However, if the kid just says, give me ice cream, now the genie could give 50 scoops of garlic ice cream, and I hope we can all agree that that wouldn't be good. So a smart kid specifies the flavors, like chocolate and Oreo, and it asks for some number of scoops, because he knows that more than that makes him sick, and the kid wants to be happy. He doesn't want to be sick. So with this information, the genie can give the exact kind of ice cream to the kid. And mathematical optimization is just like a genie. You give it variables that you want it to decide, and you specify the constraints that it must follow, and it finds the values for your variables that maximize your objective. So how does this translate to maintenance scheduling? In maintenance scheduling, we have hosts and VMs, and we ask the model to find the best times to migrate those VMs off of the host and best times to update the hosts. And it needs to do that while taking into those constraints into consideration, the ones I talked about, capacity, customer disruption, and concurrency. And the model must also find a solution that minimizes the total time to update the data center. So this is how we model it, but what exactly finds these values? Well, that's what a mathematical solver does. It gives you an interface to model your problem, and it finds a solution. Our solver of choice was OR Tools CPSAT. This is an open source project developed by Google. And the reason why we chose this solver was because it's easy to use interface for scheduling problems. CPSAT has a variable type called interval variable. And what it does is that it takes a start time, an end time, and a duration. And if you think about VM migration, it has the same qualities. It starts at some point, ends at some point, and it takes an expected duration of time. And CPSAT can also express constraints, such as add no overlap, which says do only one task at a time. And if you think of what I said earlier about disruption and customer disruption budget, that's exactly what we try to do here. So this is a very direct way of expressing the same kind of constraint. So say you have a host, and you have 4 VMs on this host, and trying to build a model to minimize the maintenance time for this host. One thing you do is you give a constraint for how many VMs can be migrated at the same time, and you ask the model to find the shortest time to update this host. The model would give you a schedule like this one. It puts the VMs, it schedules the VMs such that it minimizes the model's maintenance. So now I add another layer and color the VMs based on which customer owns it. And I add an add no overlap constraint for each customer. So you can see that VM 2 and 4 belonging to the same customer are migrating at the same time. So now my add no overlap constraint will be unsatisfied because they're happening at the same time, so it can't exceed 1. So what the solver would do is then to find another solution, which does make the host maintenance time a little longer, but it also keeps the customer happier. So this is a toy example, but the implementation is not that different when you try to apply this across hosts and apply this to hundreds of hosts. So with this powerful engine, we built a new service that's dedicated to creating maintenance schedules. Fleet Maintenance Planner creates all the data that our control plane needs to schedule the maintenance, and it centralizes who and when gets maintained and leaves the rest to the control plane. So the control plane still does all the hows, how the migration is scheduled, how it goes to the host, how it's retried, etc. And it only strips out the who and when. And this enables us to do optimal maintenance scheduling at scale. So before I show you how we placed in our control plane, let me also remind you what happened before this. Our SREs were responsible of understanding the spare capacity and availability in each of these data centers, and they would run queries against the database to understand what hosts need to be updated. And most importantly, they would actively decide every day what set of hosts out of all the potential hosts to be updated. And they would do that by looking at the hosts and understanding which customers are there and trying to make sure they don't cause disruption to anyone significantly. This is very high toil work. And how we replace this is by making SREs still responsible for declaring what versions a host should be on, but making our control plane take care of the rest. So SREs still decide what hosts are going to be on what version, and they do that with the coordination of the software teams. But our control plane takes that information and decides what exactly to migrate or update. And it does that by playing this ping pong with the Fleet Maintenance Planner. It asks for a schedule daily, and the Fleet Maintenance Planner gives a response daily. And while doing that, this new service takes feedback from the fleet. It understands the available capacity. It understands the platform health to decide the concurrency limits for the migrations. And it also understands the VMs on the hosts, because the fleet state in our data centers are quite dynamic. The customers create VMs and remove them very fast. So this dynamic nature requires us to also schedule these maintenances every day instead of scheduling all the maintenance for the next 2 months. Because that schedule would have a lot of VMs that won't even exist, and it would consider limits that won't hold true in the future. So I talked about how it may be hard to know the quality of the solution that you get if you just write an algorithm. But a mathematical model like this, it comes for free, because the model is also able to give you the theoretical minimum along with the solution that it gave you. So you get to compare, for example, how many days the solution that you got takes in the data center, and what will be the theoretical minimum. So if the theoretical minimum is 100 days and you get a solution with 105 days, you may be fine with the 5% difference or on optimality. So at this point, it just becomes a trade-off between how sensitive you are to unoptimality and how fast do you want the schedule to be generated. Another side benefit of having a model like this is to be able to do scenario analysis. By tweaking the values that go into this model, maybe in a simulation environment, you can now answer business questions like, what if we scale the data center by twice as much in a year? Or what if this customer scales 10x? Would that change our ability to do maintenance? And this is exactly how we decided how much spare capacity we need in each of our data centers, by running these numbers throughout our data centers with different spare capacity with respect to, like, as a percentage of our total hosts, and then gave the business a clear trade-off between how much money we want to spend and how fast we can do the maintenance in our data centers. So in summary, mathematical optimization can solve problems at scale. It is flexible and it allows for incremental development. And it gives you tools to answer ad hoc business questions while solving your problem day to day. Thank you.